and that we have here is X of n, this is n. Then we have samples. Here. Then we do y of n, that is x of 2. And now what y, so this one is, then this one, and this one. And there are two axes. Okay, so in the axis for x, this is sample number 0, sample number 1, sample number 2, 3, 4, or sample for the y sample number 0, but this is sample number 1. This is not sample number 2. See, there are two axes there in the mix. So the sampling rate for the green signal gives y is the sampling rate of the other one. So the sampling rate of y is twice the sampling rate of the other one. And now what we will see is this operation here is called decimation. With decimation here by a factor of 2. So in general, they like this. And okay, so this is the separation, and then we have the power spectrum of the input signal, and then the power spectrum of the decimated one. Okay, so let's remind a little bit this kind of stuff. Okay, so we have power spectrum here. It's a smaller. So let's think of the power spectrum of X of A. So we know that it goes from minus pi to pi. And because we are doing, we are taking the FFT, so the FFT also show these things. The FFT, here we have samples along the axis. So what we have are these samples. Separation here, pi divided by n. Right here, n, where n is the number of samples of x. Yeah, so now what about the power spectrum of y? Y. You also go from minus pi to pi because it's a discrete signal, and all discrete signals always go from minus pi to pi. And now it is longer. Okay, we will characterize that. Okay, and now we have samples. How many samples do we have now? So if this one has had n, this one has n half. So now the separation, two samples is 2 pi divided by n. So they are more separated. And if we think so, and in total we have only n half samples. So this is what is shown here. So the power spectrum of the original spectrum, the original image, is this big, where I have n pixels or R rows, C columns. So you have and have this size of the power spectrum. But now we have a smaller image dimension. So we have half the samples. But the extending the frequencies is the same. So this goes from -pi to pi. And here it also goes from -pi to pi. Okay, because it is a discrete signal. On all discrete signals, they always go from -pi to pi. Okay, so there is this scaling property of the Fourier transform. This first equation is just the Fourier transform. And then we have this relation. Okay, so look at these transformations. So in real space, we are multiplying by a factor. Multiplying or dividing by a factor is the same. So if you want to multiply by something, you simply divide by 1/2. So you have I, now you have a linear transformation of your coordinates, and then the Fourier transform of this transformation will be the Fourier transform of this one, and then so the original Fourier transform, but now the frequencies they have been scaled. So if these are divided by A, here is multiplied by A. And here you have this factor. Actually, this is a real. This is a particular case with more general relationship. That is this one. So let's say that we have an image I. So you have an image I. We have a Fourier transform. Now, you have a new image that is AI, and this A is a matrix. Okay, so you are transforming this one. Now, the Fourier transform of this is 1 divided by the determinant. Okay. So this is a more general case of the equation that we had in the slides. So this applies to any dimension, any matrix, any transformation. While this one is only for a particular case. It is a particular case where A is equal to 1A, 1/B, 0C. The one in the slides is for this particular case. This is the more general case. But we may look at these things. So you may remember, let's go for 1D. Let's go again with 1D. So let's make the estimation. So for the then estimation, you may remember this. So what is this expression? So how would you say what has happened to Y with respect to X has compressed? Okay, so originally X had n samples, now it has only n samples. So it has compressed. So there is a compression in real space. And if there is a compression in real space, what should happen in Fourier space? Should expand. Should expand. So Fourier transform of Y transform of Y is there are more terms, okay, but the important term is this one. So this is compression. This one is compression. This one is expansion. And that is what I was trying to plot here. So there was an expansion between these two spectra. Okay. So this one is at pi and minus pi. This one doesn't vanish. It vanishes where? At pi. We continue. same as -5. But there was another copy at 2π. There are more terms here. That the other terms are simply just to make this periodic with period 2π. But this one here also expands. It expands to 0. So here you see the aliasing. So here is the aliasing. What we say here? Coming from the nearby copy is invading our central copy that is between -5 and 5. And this area here is the one causing the aliasing. And it is because of this expansion. I'm compressing in real space, I'm expanding in Fourier space, and then there is aliasing. We compare this to this one, see the same kind of relationships. So this one here and this one here, they have opposite signs. So if there is a compression in real space, there is an expansion in real space. There is a -1 there. So these ones, they have opposite signs. It is the same. Okay. Exactly. Okay, so there is this. This is called the scaling property of the Fourier transform. This is just a reminder of what we have said. Something is compressed in one space, it is expanded in the other one. And there is a aliasing happens in time. So we have seen the aliasing for images, but you know, aliasing also happens in time. This is obedience. Look at the hey. It really doesn't seem to be. And this should be this possible. Generally, they shouldn't have. But the reason why it doesn't move is that there is a sample. Okay. It's moving. That's fine. So let's see. Let's see how to understand that effect of the grid. So let's say that this is the position of solidified grid. Let's look at this point in the grid. So it is turning. So at the beginning, let's say that at t equals 0 is there, and then it is turning. So as it's turning, it goes down, and then it goes up, and it goes down. Actually, it is a pure sine. And then we are taking samples. So let's say that your sample is that you take a sample here, and your next sample is here, and the next sample is here again. So it seems that it doesn't move. Let's say that you take a much finer sampling. So you take this sample, this sample, this sample. So now you can see the wheel moving. And so it is a matter of sampling. So the same happens. This was in time, but the same happens in space. Okay, so we have seen aliasing in one dimension. Aliasing in one dimension was this. Was this important? So the central copy is expanding, but the nearby copies there also expanding. So let's see these effects now in Fourier space and for images. So now we are with images. So our spectra. Say that this is the 0, 0 frequency. This is omega x, this is omega y. I, this is range, and this is also pi. Range, right? I will concentrate in one of the sides, but it happens everywhere. Okay, so we had the same. Okay, let's say that we have this spectrum. Let me be consistent with the colors. So our original signal was black, and we had another copy here. We had another copy, and so on. Now, so this is the spectrum of our image. Now, I have my downsample image. My downsample image. I have to expect that is omega half. So this omega half is making it bigger. So now this one will be bigger. But this one will also be bigger. And then everyone is becoming bigger. Twice bigger. So this one that goes pi goes bigger to 2. But the effect is this one. Everyone now. So let's say that we start at this one at 0, 0. Now everyone becomes bigger. So this was the central copy, and then this copy at 2 pi, it also becomes bigger. Now there is an overlap. And the amount of overlapping here is smaller than 4. Because we had a spectrum that was smaller. Okay, so let's see. So if we do a downsampling by a factor n, then everything, the decimation by a factor n, everything enlarges by a factor 1/n. Okay, so let's see. So why do we have that? So let's come back to our one signal. Okay. I do the reason is in 1D because they are similar. So this one. Now we want to produce the ones that are 1/2. So this I can say y that is some rescaling of the axis that we are not taking care of at the moment. But this one is this multiplied by a train of deltas. This one. This signal is called pi. So this is called a Coulomb function. It is called because it looks like a Coulomb. So, and this picture is the sum a minus infinity delta n minus. Let's say that my Coulomb is size 2. Separation between these two is n. So if y is a multiplication of two signals, what happens with the Fourier transform? Fourier transform y is Fourier transform x composed with the Fourier transform of the cone. You agree? Because it is the multiplication of two signals in real space, then in Fourier space, it will be a convolution. So now we have to wonder, okay, what is the Fourier transform of the cone? The Fourier transform of the cone is another cone. It's another cone. Something. Infinity delta, but now we are in Fourier space. And if that is n, so it is another cone. So what we are convolving is the original spectrum with delta functions that separated now by. So yeah, so all this reasoning now is in the slides. So we have the code in real space. The argument is real space pros and cons. And we are multiplying the original signal by the code. It's the original signal times the. And this is the same. And now this is a reminder of if we are multiplying in Fourier space, then we are convolving Fourier space and the opposite. So if we are convolving in real space, we are multiplying in Fourier space. And then this is the Fourier transform of the code. Now you see the argument is frequency. There is something important here, please. Okay, so it is another code. Now, if you conform with a code is set of deltas. So if you conform with a set of deltas, what you are doing is really your original spectrum. Original spectrum was this one. You're really into the location of each one of the deltas. So yeah, this is just a reminder of that. When we are convolving this spectrum with this delta, you have to read this spectrum, the location of the delta. And because you have many deltas, all these many deltas separated by 1 over n, then you are taking this spectrum and moving it everywhere. This spectrum enlarged, okay, because of the downsampling. So if there is no aliasing, okay, so let's say that my spectrum is that. Let's do it in one week. Okay. If the drawing is less than that I expect. But my spectrum is such that it goes only from -5 half to 5 half. That's clearly happens the same. It's only so when I do the downsampling, the decimation will enlarge. But it will enlarge by a factor 2. But then these will go to 5. That is no alias. This one will also enlarge. But it will stop at 5. Remind always to label your axis. cannot leave axis without lasers. So if you look at that before or doing the decimation, your spectrum is restricted to pi divided by n minus pi divided by n. There will not be any aliasing. And here you have again the anti-aliasing filter. Before doing the decimation, it's important to do an anti-aliasing. So like this, you guarantee that once you expand, there will not be any aliasing. Let's say that my filter at the beginning, my spectrum at the beginning was like this. Say that was going minus pi to pi. So where you apply the anti-aliasing filter, so these will be removed. And then you do the decimation. Then when you do the decimation, spectrum will be like this. So there is no aliasing. So before doing the decimation, it is very important to do the anti-aliasing. Yeah, so the first one was not necessary, and so you put it, but everything passed the filter. And here is a different example where not everything passed the filter. Okay, so here you have an example where there is no aliasing. So you have after the expansion, you see that the spectra do not overlap. And for that, you need this condition. This condition is this one. The spectrum has to be smaller than pi over n. So it depends on what is your definition of the axis. This will be pi over n, or 1 over n. Yeah. This one's good. Which is your question? Why there is no aliasing now?
Yes, but why is
So this is before decimation. This is after decimation. No, porque cuando tú haces el decimado, el espectro se expande por 2. Se expande por el factor n. Entonces, si tú haces un decimado por 2, se va a expandir por 2. Entonces, pi medio se va a ir a pi. Did you see all these things in the linear systems course? It is those are the same ideas, but now in 2 dimensions. So yeah, and all this is this thing of where I put my focus. So these signals are periodic. So these signals are periodic. So that means that I can do from here to there. I have one period, for example, from here to there, they still have one period. So you may remember this is the one of FFP. Computers like this one. But the one that goes from 0 to 5, and humans prefer this one. For the frequency is similar respect to 0. Depending where you look at, this one is going from 0 to 5. This one is going from -5 to 5. And then this is when there is aliasing, this is when there is no aliasing. After the expansion, so all these spectra are after the decimation. So when there is aliasing, when there is no aliasing. If there is no aliasing, it expands. In this case, it's this one here. This case is this one. After the expansion, it perfectly goes from -5 to 5 to 6 here. And then if you look at your sheet to go from 0 to 5, then this is what you see. This is one of them. We will come back to this representation in a moment. But we already introduced it before in the lecture of Fourier transform. Okay, so let's see how to do the anti-aliasing filter. So the anti-aliasing filter here. So the anti-aliasing filter to be, if I'm doing a downsampling by 2, it has to crop half of the spectrum. All this half of the spectrum has to be taken away. And it is an anti-aliasing filter, so it is how the signal flow. Have signal or the image goes to the anti-aliasing filter. And then we have here the form. Then we do the decimations. Decimation, that's presentation. Decimation of this. Here we have like this. So these X says the convolution of the X with the impact response of the anti-aliasing filter. This is one way to do it. So you have to design your kernel and then you convolve, or alternatively, and take a Fourier transform of this, multiply the Fourier transform of the input times the Fourier transform of the anti-aliasing filter. Then you do the inverse Fourier transform. So either you do the convolution in real space or you do the convolution in Fourier space, whichever you prefer. Once you have convolved, you do the decimation. Okay, so this is what we are doing. So we have to design a kernel to do the anti-aliasing filter, and this kernel can be, so let's say that this is our large spectrum. This large spectrum is this one. Is this one. This large. And then the purple one, the purple window, will be our anti-aliasing filter. So you have to take this window to the inverse Fourier transform. So this is in Fourier space, and you do the inverse Fourier transform. It will look like some function. Actually, if this is in Fourier space, this is a kind of a step. So how does it look like in real space? So if you have a step in Fourier, what do you have in real? See? Okay, so this may look like a scene, a two-dimensional scene. So your kernel would look like a two-dimensional scene. And then you may crop. This is what is discussed here. You may crop your kernel. So the sink goes from minus infinity to infinity. We have to make this convolution, not necessarily, so you can crop your kernel if you want. And then let's see how it goes. So you have your original image. This is the original power spectrum. Then you do the anti-aliasing. So now we have multiplied by this. See my new kernel here. We are multiplying by it. So we are setting it to zero, everything outside. And then you do the decimation. This is with a different anti-aliasing. So instead of just this ideal function, you can put the Gaussian, and it is also anti-aliasing. So you can put the Gaussian with the appropriate width. And then this is with this Gaussian, this is the result. And then you do the decimation. The decimation will expand. But the decimation will make this spectra. So originally, this was minus pi and pi. Now, after the decimation, this point will be minus pi and this will be pi. After the decimation. Okay, so you produce your decimated image and then you expand it. Now you don't have anymore the aliasing. And probably this filter was strong because you were removing quite a lot of signal here. So you can apply anti-aliasing filter like this. And this will cause a little bit of aliasing. So because the extra copies, so you see the copies outside, you're not completely setting to zero, so it causes a little bit of aliasing. Now, see, there is a little bit of aliasing. It is less blurry. So this one is too blurry. If you look at the edges, it's a little bit blurry. This one is less blurry, but there is aliasing. There is aliasing because outside you're not setting to zero. So all this energy, when it expands, will go into the central area. So there is a compromise between making, if you do it with Gaussians, making it too blurry or allowing for a little bit of aliasing. And this is with the ideal. So with the ideal filter is the step one. So step one is really good in this case. Little with Gaussian, there different kind of Gaussians. And this is without any anti-aliasing. So this is the worst. This is the one that has the largest aliasing. Any question after the end? Okay, so let's see this expansion. This explained with the torus. I find the explanation with the torus a little bit confusing. So I think this one is more clear. Okay, so let's try to do it. So let's say that this is our axis, x, y. I will do it only with the horizontal one, because otherwise it becomes too minus pi, this is pi, pi, this is pi. This is minus pi. Let's put numbers to this all these regions. So let's say that this is the 0, 0 frequency. So let's say that this is region number 1, number 2, number 3, 4. Check if I'm following the same region. Then 5, 6, 7, 8, 9, 10. And here we have another copy, the same layout. Another one with exactly the same layout. Okay. And then we'll do something. So let's say that we don't do any anti-aliasing filter. So all the regions will expand. Anyway, all the regions will expand. The difference with anti-aliasing is that all this frame will be set to 0. All those values will be set to 0. But anyway, they will expand. Only that we are defining zeros. Okay, so we'll do that after the break. We make break and minutes. Okay, so today we will extend a little bit our concepts about sampling and what is the effect sampling and Fourier space. And you already know that one of them will be aliasing. So let's think a little bit more about these ideas. So here we have an example of aliasing. So let's say that you have this image. It has a given size, and now you do a decimation of this image. So you take 1 every 2 pixels and in both directions, and then this is what you get. And now if you zoom in, now you see that this front of the frame has a funny pattern that was not there. So this funny pattern here is aliasing. And aliasing is something that happens in high frequencies. And this is high frequency. So this is high frequency because it has a very small details. And then this is where you see these effects. Okay, so if I expand it, pi goes to 2pi. Now it occupies only. So it is expanded by a factor 2. Pi half goes to pi. Then we have all the rest. Okay, so let's put the same numbers. So now this is 1, 2, 4, 10, 5, 6, 7, 16. Okay, so all we have done is the central copy. The central copy we have expanded by a factor 2. So instead of going from minus pi to pi, now it goes from minus 2pi to pi. And this central region that was going from minus pi half to pi half, now it goes from minus pi to pi. Yeah. They are exactly the same values. Yeah. I started counting in the other direction. So, so now they have expanded. Okay, let's keep track of the other one, the purple one. So the purple one also expanded. And it expanded, so Now it will go from 0 to 3 pi. So 3 pi, we don't care. Let's look at the one and see what it will go. And this one will also expand. So we'll have 1, then 2, 3, 4, and then let me do it like 5, 6, 7, 8, 9, 10, 11, 12. Everything will expand. Okay, we are just plotting one of them, otherwise we become crazy. Okay, but everything, there are infinitely many copies, and each one of them is expanding by a factor 2. And then let's look at this region. So this region is having a copy from the central region, but it is also having another copy from the nearby region. You see? So the region from 0 to 2 pi, now it has two contributions. One is from the central copy that has expanded. The other one is from the right copy that has expanded to the left. And now we have the addition of the two. And here you see the aliasing. This is aliasing. This is aliasing. Okay. This is aliasing with the right copy. And if you do the same flow with all the other copies that are expanding, then this is what you get. Okay, so this is the central expansion, but then this is the one on the right, the one on the left, the one top, the one below. And then if you keep track of everyone, this is at the end what you have. So you have the contribution of the central copy that has expanded, but the contribution of all the nearby copies that are also expanding. We have only reason one of them. We cannot do. We can do everyone, but it is too confusing. Okay, we have just reason the right copy that is expanding. But if you keep track of all the other regions that are also expanding, so this region here that we reason had the contribution of 1 and 10, will also have the contribution of 1, 10, 12, and 15. And this one will have the contribution of 4, 7, 9, and 11, so on. So each one of the regions, now it has 4 contributions. And 4 contributions because we are expanding by a factor 2. So if we are expanding by a factor 3, or decimating by a factor 3, then we would have 9 contributions rather than 4. So you can do the same reasoning on the totals. This is yeah. Yeah, because we have reason that this central right copy is contributing to the central one. But what about this one? This one is also expanding. So it will also have a contribution there. These are not pixels, these are regions. Well, originally, I'm not formally represented, but originally we had 10 identified 16 regions. Then the 16 regions after the expansion, then will become 4. Then we are tracking who is contributing to these 4 regions. And the contribution here we come from the right, from the top, from that diagonal, and from this diagonal that is used. Okay, so at the end, what we see is that is a lot of aliasing. We are saved by something. Aliasing in principle shouldn't be so important for one reason that we mentioned the other day. That is all the spectra that so all the spectra by plotting it in one dimension. So all the spectra, if I plot one dimension, behaves as 1 over omega squared. So that means that the energy at high frequency, that is the ones that are the copies that I'm getting. So in this plotting that I'm doing, here would be region 1, this would be region 10. So the energy that you are getting from region 10 is small. Okay, but depending on what is your image, can be not so. That is why we are having aliasing. This aliasing is because for this particular image, the energy at high frequency is not so small. It is not so small because we have very fine details. But in general, should be small. So aliasing is not such a big issue. Not always. It depends on what is your image. Unless you do this anti-aliasing filter, this one here. Once you do this anti-aliasing filter, we will click here. This one that is setting everything to 0. You all this energy would get into your center node. So now we are done with aliasing and sampling. So let's continue a bit more because we will not have class tomorrow. Let's continue. We have a lot of time. Okay, so next lecture is about resizing images. So resizing images is we want to change the size of our image. Somehow we have done that here. When we were making the decimation, Here, this one here. We were reducing our image by a factor 2. So now let's do it by any factor, not only integer factors. So let's do it by any factor. And that is this idea of resizing, and the main topic here is interpolation. Okay, so how you make the numbers in your final image if you change the pixel size by an arbitrary factor. So here in this example, we will change so we were changing the pixel sizes by an integer factor. So now let's not make it integer. So now there will be an arbitrary relationship between the pixel sizes. And then what we will see is that you have to come out with the values, and these values will be given by any one of these interpolators. Okay, so let's start with, let's make images bigger. Okay, so I'm making images bigger. So I have an image. This is I want to go through some transformation that makes it bigger. So if the sum pixel size here is yes, what is this sampling this new image? Is it bigger or smaller? It's bigger. It is smaller. This one here divided by 4. By making 4 times bigger. So now the pixel size will be smaller. Okay, so how do we do that? So let's see. We know one particular operation for that. Already know. So before we were doing decimation. So what is the opposite of decimation? Abstraction. Now we do an abstraction by a factor. And let's make it for 1 digit. That's why if let's make it 1D. There is no doubt about the argument. It is not necessary. So this is I over N divided by M. If N is multiple 0 other values. Okay, so let's say that this is our input image. Let's make an expansion by a factor 2. And then I have this value, then 0, then this value, then 0, this value, then 0. So I'm doing an expansion by a factor 2. This is this operation here. We are doing by a factor 4. So I have a value, so I have this image, and I'm making an expansion by a factor 4. I have a pixel, then 0, 0, 0, 3, 0. Then another pixel, another 3, 0, and so on in both directions. We are doing the same operation. This is an upsampling by a factor 4 in both directions. Okay, so now let's look at make a zoom there. So we have a pixel, 0, pixel, 3, and then this is not a good representation of the original. The original looks like this. The expansion looks like this, which is not a good representation. So now what we can do is just to replicate. So we have these values with dots. We have this value and replicate 4 times in all directions. So I have to replicate 15 times. If I have this dot, then I replicate. So that replicate. What is that? That is here. So we have a signal go through the upsampling. Then I am convolving the reconstructions. Now my reconstruction here in 1 dimension. Fraction of n. I'm convolving whatever comes out from here, I'm convolving with this fragment. And then this is my reconstruction. Then this is my expanded image. So replicating is convolving with a reconstruction that is just a step. To the whiteboard? Yeah. Okay.
Has to be for the class, the instruction.
No, if it is by a factor of 4, it doesn't. Okay, so now let's go in the other direction. So now instead of replicating, so instead of making it bigger, we will make it smaller. So this is decimation. and this we already know. Let's say that this is our original image. Now you take 1 every 4 pixels. This is just something, and then you put it there. So as it is explained there, as it is explained, what we are doing is just this. You have an image, then you go with down something by and that's it. And we know already the problems. So if you don't want to have problems, we have to put here is an anti-aliasing filter, but we haven't put it. Okay, so for the moment we haven't put it. So the way it is explained in the slides, it is just the decimation. And then this is called nearest neighbor. So this idea of for integer decimations or upsamplings, now we can expand something called the nearest neighbor receipt. Okay, so let's say that we have this image and we want to change the factor, the sampling rate by a factor of 3/7. So let's see how to do that. Okay, so first, this is a very graphical situation. So first, let's say that this is our original image, and we want to make it smaller. So we divide in blocks of 7 times 7. Now we take pixels, 3 pixels in those blocks, and we try to distribute as best as we can. So we put 1 pixel, 0, 1 pixel, 0, 1 pixel, and now 2 zeros, because we cannot evenly distribute 3 pixels in 7. And then we simply take these values. We take the values from the yellow boxes, the yellow pixels, and we put them together. Okay, so we keep those, then we put them together. This is our new image. This is the result. So now we started with something. We produce something that is 3/7 of the original size, and this is how it looks like. So this is somehow a generalization of the upsampling and downsampling operators that we work on now by a factor that is not integer, it's just a fraction. Let's say that we go in the opposite direction, 7/3. So now we have a small image and we want to make it bigger. So what we can do is something similar. So you take blocks. Oh, nice picture. So, but you take blocks of 7 times 7, so it is the opposite of this. Okay, so in the output, you create blocks of 7 times 7, and then you will fill these 3 pixels of 3 times 3 pixels from the original data. All the rest are 0. And then you copy the nearby pixel. Then yes. There is not such a nice picture here, but you can really see. So you have the blocks 7 times 7, then you fill the 3 times 3 blocks, and then there are holes. You have this thing. So there are holes. Now you fill the holes by simply copying the nearest pixel. Okay, so in general, how you do? Okay, so let's say that you want so in general you have input image that has R rows, C columns, and it will be I. Now we want to transform it. So something that has R prime, C prime. It would be our I prime image. Okay, so these are the coordinates in the input space. These are the coordinates in the output space. Okay, so I want to produce this image. This body. Where should I take it? I should take it from somewhere here. Where? What about this big? When you take the RC prime and the coordinates. And now let's see if it works. Okay, so let's say that I have the 0, 0 coordinate. 0, 0 coordinate. You plug it in there, and you make this calculation. 0 is goes from 0, 0 coordinate. Okay, what about this one? So this one is 0, 0. 0, 0, you are taking from 0, 0. Okay, what about this one? I want to copy that one. Okay, that one is a this is X, this is Y, this is X, this is Y. So that is C prime, C. So this part will be 0. What about this? So this part, this is capital C. These are capital, these are small. So C prime cancels with C prime. I have to take it from C. I have to take it from C, 0. And you can follow all the rest. Follow. It's there. It's 0 R prime. I have to take it from 0 R. That's one. Running out of the this one that is C prime, C prime, R prime. You are taking it from C. So it seems that this transformation it works. Transformation is working. So what we are simply doing is you take the coordinates in the output space, you multiply by a scaling factor. It's a scaling factor. And then you are getting the coordinates in the output, in the input image. So these are the colors. This is it's an RC coordinate. C coordinate. This is R. This is C. So you take coordinates in the output space, multiply by something. You have coordinates in the input. So what you have is a transformation. Let's make it here. So you have I, then you have coordinate here, R prime, C prime. And you are applying the transformation. Find every coordinate in the output, where it is coming from in the input. Okay, but there are tricks. Right, there are tricks. Because let's say that I have, let's put this in numbers. Okay, so I want to compute for this there, I prime. It's I prime at the location pi, pi. And my factor, let's say, is 7/3, as in the examples before. So I have to copy this. So 7/3 pi times 7. Do I have this value? Or I don't? If I ask you what is the input image at this location, do you have it? No, why not? So I want to produce the output image at the location 5,5. My scaling factor is 7/3. Then I simply have to copy I at this location. Do I have this value? I don't have it. Because it is an integer, it is a non-integer value. So it is like that. I want to evaluate that. But this, I make it 1 bit. Okay? So have x of n as values. So I have them at 0, 1, 2, 3, 4, 5. But I want to evaluate in the middle of two samples. I don't have the value at the middle of two samples. So I have to do something. What do I have to do? What do you think we can do? Upsampling. Okay, upsampling is somehow here, the scaling factor. So I'm asking you the sample at this location. You don't have it. Which one would you take? Rounding. So either you take 4, you take 5. So you have to round. Either you take 4 or you take 5. Now you get the name. You name this. There you go. So this sample will have one of these two will be the nearest neighbor. So I take the value from the nearest neighbor. That's it. Okay, so all this reasoning is the one in the slide. Okay, the slide is a little bit complicated because it includes this -1. Yes, depending on whether R and R prime is one bigger than the other. The opposite. So this is a little bit too detailed for what we want. So the important thing is this one. So you have R prime C prime, the output space. You multiply by a scaling factor. Then you have a fractional coordinate in the input. And then the fractional coordinate in the input, you have to round out. Otherwise, you have to round. Then what you say, the output at the location R prime C prime is taken from the input at the location, at the rounded location. All this is, now it is the same idea explained over and over. So here is this, for instance, let's say that this is my input space, and I'm doing a factor that is a little bit larger than 1. So this scaling factor is a little bit larger than 1. So the separation between one sample and the next will be a little bit larger than a pixel. So a pixel in the original image is too small, and I have to take it a little bit farther. Okay. If this is the case, the output image will be smaller or bigger. The output image will have more or fewer samples than the original. Fewer. They have fewer samples. So they are separated more than in the original signal. So we are doing a downsampling or an upsampling. Downsampling. We are doing the downsampling by a non-integer factor, that is this one, R divided by R prime, C divided by D. And this is the opposite. So the opposite is now we are doing an upsampling. So the pixels in the output, they are closer than the pixels in the input. And then there are considerations about what happens in the borders and so on. Borders we don't care at the moment. We don't. So yeah, so the main thing is this idea. All this is just what happens in the borders and examples. The main thing is this idea. So you have to round. There is a scaling between coordinates, and then because you are getting fractional coordinates, you have to round. And then, do you remember that we were replicating at the beginning of the lecture? So here at the beginning. We were simply replicating. So this replication can be very easily put in this framework. So in this framework, this replication is this one. So what if instead of rounding, we take the floor of the fraction? This is a replication. So what we were doing at the beginning of replicating 4 times the pixel value, if you take the floor instead of rounding, it's a replication. Okay, so now let's see. So I think there is a better. So pixel replication was having this kind of responses. Now, can we make it smoother? So why making this very sharp transitions between? So we had originally we had a thin lash, we make it bigger, and now we have these kind of big pixels. Actually, these 4 times 4 big pixels. So can we make a smooth transitions? And the question is the same as, okay, so let's say that make this bigger, okay, this growing. This is exponential. Okay. I have a sample. Now my samples are very separated. 0, this is 1, this is 2. And I'm asking you for the value. I'm asking you for the value in this location. So in this location. So why simply rounding? So rounding would give me this value. Let's say that I ask you at this location, and it would be this rounding. This location is this rounding. And then at some point, I ask you at this location, then you could give me this. See, and there is a very sharp transition between the two. This is unnatural. Why don't we do something different? So why don't we join by a line And then the samples that I have to give you are these ones. And I have a very smooth transition from these variables, from x0 to x1. So how would you call this? Green, what? So this was Nevis interpolation. Yeah, nearest neighbor interpolation has very sharp transitions at some point at 0.5. Make a sharp transition in your response. How would you call this one? Interpolation means inventing the values. So you don't have the values in between. Then you have to invent them. This is called interpolation. So how would you call this one? Linear interpolation. So what you are doing is fitting a line, then you evaluate fit a line, then you evaluate the line at the location you want. Okay. This is in 1D. And now, if we are in images, you will have to make an interpolation in two directions, and then it is called bilinear interpolation. You are doing in 2 dimensions. So this is a bilinear interpolation. So bilinear interpolation will make a smooth transition between the samples you have. When you have this sample, you have this sample, then you will do a smooth transition into the two. The two has the same value, so it doesn't matter. But now this one and this one, they have different values. Then you are making a smooth transition between the values. Okay, so let's see how bilinear interpolation is performed. So let's say that we want to upsample by a factor 2. So upsampling by a factor 2 means you have a pixel, then 0, then another pixel. Okay, so have a pixel, 0, another pixel. So, and you have the values or the pixels in the corner. And then I'm asking you, what are the values of the image in these locations where you don't have it? So let's try, so for instance here, I want to evaluate what is the value there. So how what I can do is, what I was doing here, I had two values and I was fitting a line. So now I have 4 values, but I can fit this a plane. I can fit a plane and then evaluate that plane in the location you want. Okay, so let's get that. Okay, so this would be the result. So you have fitted, you have these 4 corners. Now you have to evaluate in this cross. And you have fitted the plane, this plane. And then you evaluate the plane, these 5 locations. And you have a smooth transition between the 4 pixel values that you have. Okay, so let's see an example. So let's say that we have this image, we want to enlarge by a factor 4. So this is the result with bilinear interpolation. Let's see the eye. And then, so let's see how to do that. So first you make this expansion by a factor 4. Now you have 3 pixels in between non-pixel values. So you have a pixel value that you know, 3 zeros, another pixel value that you know, 3 zeros, and so on. So these are the ones that I have to validate. And how this is represented that. So I have I know this value, there's 3 zeros, another one that I know, 3 zeros, another one that I know. So I fit the plane between the 4 values that I know. and evaluate the plane in all the locations that I know. Then this is what you get. But this is the result with linear interpolation. So this is the result with nearest neighbor interpolation. This is the result with bilinear, which is much smoother and it is better. So this is with fixed applications, and this is with bilinear interpolation. Which one of the two do you think would have more aliasing? This one. This one has higher frequencies. You are making sharp something. You are going very quickly from one value to the next. That is higher frequency. Higher frequency. This higher frequency that is artificial is aliasing. Nearest neighbor interpolation has aliasing required. Bilinear interpolation doesn't. This is again more. So when you have to evaluate these darkings, so the equations have the same. We are making a change. So we are going from one coordinate in the output to one coordinate in the input. It will be the fraction, a fractional coordinate. But then when you have to evaluate what is the input image at that fractional coordinate, you are using this figure of fitting planes. We will have these next. Any question? Yes.